Recording. All right. Happy Friday. As a Friday treat, we are doing regression. We're starting regression, which is, I like to end on a high note. It's fun. It's relatively easy and very little hypothesis testing, very few confidence intervals. There are lots that we could do, but we're not going to if I can help it. So here we go. So it's just fun. We finished chapter 7 last day, which I guess was yesterday. And that's on quiz 4, which is on Tuesday. So maybe I should, for anyone who's reading these notes after, quiz number 4, which is on chapter 7 on Tuesday. And because I can, makes it look like I have that cool writing, maybe. I don't think I could pull it off. It would take me hours. Okay, chapter 8, linear regression. When we say regression, really what we mean is line of best fit. And linear, of course, means line. So it's a straight line and a line of best fit. So if you prefer to think of it as line of best fit, that is totally fine. Okay. I remember in, I think it was probably chemistry 11 or 12 or something, and we had these data points. We had hand drawn a scatter plot, and then we were just supposed to fit the line of best fit. But what we did, we just took a ruler and we just drew it. It's a little bit more complicated than that, obviously, and so that's what we're going to get into. But the idea is the same, right? We draw a line that captures most of the activity, and that's our goal here. Okay? So linear regression models the relationship between a numerical response variable and an explanatory variable, which is often numerical as well. It can be categorical, but the key is that the response variable is numerical. Okay. So linear regression models the relationship between a numerical response variable and an explanatory variable, which is often numerical. But I don't want to specify because it is allowed to be categorical, but it's often numerical. And so what we can do, and these terms, right, the response and the explanatory variable, that's drawing from chapter 1, right? That terminology that we kind of grilled in and then we left it alone. And here we're ripping open old scars, I guess. Chapter 1 scars. The response variable is your y, right? And your explanatory variable is your x. That's why I like to use the term explanatory, because it has the x in it. Okay. Yeah, so if you want, you could say that this is the independent variable and the y is the dependent variable. But for me, what I find, and you have to think about how your brain works, right? But what I find is that I have to put a lot of thought into which one is which. And so that's not helpful to me. So I use this response explanatory terminology, but both are fine. I've even seen mashups, dependent and explanatory. Wow, Emily, that's so weird. I know, right? I know. All right. Now we've seen it briefly, but how we visualize this relationship is with a scatter plot, right? And we've all seen scatter plots, but we're going to talk about them some more. So we can visualize this relationship with a scatter plot. And from the textbook, I want to use boom, little elevator music. All right. Okay. Oh boy. Where is it? There it is. We're going to do a kind of referring back to data about this brush-tailed possum of Australia. And here it is, little cutie, I think, although it looks kind of mean. But maybe it's just the flash. Why are his eyes so red? I don't know. Anyways, that's what we're going to be talking about. And what we can do is we can see the scatter plot. My pen is not keeping up with my quick moves today. Yeah. Oh, and I should grab the blurb about what it is we're looking at. And let me bump this to the top. Come on. And you can't even see what I'm struggling with because it does this courtesy hide everything that's not meant to be shown thing. It's weird. I feel like that's an update that they did. Or I haven't been paying attention. That's a possibility as well. Okay. Look. Work with me. Okay. Brush-tailed possums are a marsupial that lives in Australia, and a photo of one is shown in figure 8.4, which we saw. Researchers captured 104 of these animals and took body measurements before releasing the animals back into the wild. We consider two of these measurements: the total length of each possum from head to tail and the length of each possum's head. This is going to be one of those scenarios where it's not obvious which one is the response and which one is the explanatory variable, because, right, we've got the head length, which probably depends on how long the overall length is, or the overall length might depend on the length of the head, right? So it's not obvious which one is which, but in those scenarios, usually we are given the scatter plot. And here we're told to use the head length as the response variable and the total length as the explanatory variable, right? So the total length, we suspect it'll help us explain changes in the head length, right? And also that there is a relationship between these two, which is not that far-fetched, right? And so here, let's jot down that this is your response because it's on the axis, and this is the x-axis, and so this is your explanatory variable. Nice. Oh, question? Let me see here. Go back here. There's a chat. Oh. Okay, probably not that. All right, great. Let's see here. Oh, took an accidental screenshot. I don't want to save to photo. In fact, I want to delete that screenshot. Go back to what I was doing. Got thrown off. Someone unmuted. I thought it was a question. All right, here we go. So if we have a scatter plot, then we know which one is your X and which one is your Y. That is going to be super important on the super quiz, our final exam, because the final exam is the first time that you're going to be tested on regression, right? I like to do that because it's kind of the breeziest chapter I find, and there's a lot of gimme marks in there, and so that's how I like to end it. But it will be very important to know which one is your X and which one is your Y, because they're going to show up in our formulas. And so then you need to know your X bar, your Y bars, your SX, your SYs, right? Each of these variables is going to have a mean, a standard deviation. We're no strangers to that kind of stuff, right? So, but you do have to keep them separate and keep them under control. All right, so when we have a scatter plot, we talk about 3 things to describe it. So to describe this relationship, we talk about 3 things, which we've seen before with histograms as well, right? We talk about shape, center, and spread. Once we've covered those 3, then we have described the whole distribution. Same thing here. So to describe the relationship between X and Y, just generically, right? The explanatory variable and the response variable. We discuss 3 things: direction, strength, and shape. Shape or form. I use shape because I used shape for histograms, right? And so for me, I just like to boil it down a little bit. But first, let's talk about what our options for the direction are. There are only 2 options. Either it's positive in general, so it looks like this. So this is a positive relationship or a negative relationship, which goes down. I guess the 3rd option, which is not really an option that I want you to use, so should use red or something. No relationship would look like this. So we don't really use this one, but that is what no relationship would look like. Why would it be no relationship? Because it doesn't matter what value of X I put in, the value of Y is going to be the same, right? And so it doesn't matter, there's no relationship, right? Whereas here, if I put in a low value of X, I get a low value of Y. If I put in a high value of X, I get a high value of Y, right? And so on and so forth. So then there are relationships. All right, in terms of the strength, oops. You can have a strong relationship, which is when all these points are close together, or a weak relationship. When I'm from freehanding relationships, they're always positive. be on the sunny side of the street type of deal. Something like, there. Here we have a weak relationship. You know what, I'm gonna remove some of these because there's still a relationship. If it's just a cloud, then it would be no relationship, right? But here there is, you can kind of put some bands around this and see that there's something going on here, but it's weak, right? There are kind of gradients between here. You can go moderately weak, moderately strong, right? But in general, just classify it as weak or strong. And we're gonna have numerical measurements that we can rely on as well. Third one, the shape or the form. It's either linear or really anything else is nonlinear, right? Can you describe it with a straight line, or will it not work, right? To describe this relationship, if this is the general motion that you're seeing in your data, right, then drawing a line of best fit is not a very good model, right? So remember, when we're doing regression, we're modeling the behavior of the data, right? And just as before, we don't care about fitting the model exactly to our data set, right? That's just our sample. What we want to have is something that I can transfer and I can use to a new data set or to make future predictions of things I haven't seen before, right? And so when we build this model, it would do really well predicting values here and values here, but nowhere else, right? And so that's not a good model. You can use it, and R will let you fit a linear model to something that looks like this. There's no safeguards in place, but you should be looking for anything that you could fit a straight line to. Now, for us, we are only going to consider linear relationships. Okay? And so here, a linear relationship is a relationship that can reasonably be modeled by a straight line. Huh? So in this course, we're only going to talk about linear regression, right? So all of our assumptions or all the things that we're going to learn assume we have a linear relationship, okay? And so in this course, we will only model linear relationships. So so a linear shape is a condition that must be met. I got there eventually. There. Yeah. You're not going to fit a linear regression model to something that doesn't look like a straight line. Okay. The reason we start with linear regression is because even if you do find that you have something that looks, you know, something like this, right? Then what we do is we do a transformation. So you can transform your Y usually. And it turns into a straight line, right? Or you can transform your x, but usually you start with your y, right? So often what we do is if we don't have a linear relationship, you make a transformation until it's linear and then fit a linear model, right? And so kind of sneaky. But that's why we need to be really good at linear regression, because we'll be able to use it even if it doesn't apply explicitly. So if the relationship is not linear, we usually transform, and there's lots of rules of thumbs for, okay, if you see this shape, then you're going to take the log of the y, or if you see this shape, then you do 1 over x, that kind of thing. And so there are lots of rules, and just be aware that they exist, but we're not going to apply them. If the relationship is not linear, we usually transform the variables, potentially both, until it is linear, then model with linear regression. But then you have to transform it back for your interpretation. So it does have that added element. Okay? But can I say untransform? What's the opposite of transform? I'll put it in quotes, then I can write whatever I want. Them's the rules. But untransform the variables to interpret the output, or to interpret the model. There. Oh, that's clever. Yeah, I guess. I don't know. I'm sold on untransform. Yeah, patent pending. Yeah. All right. So we can make a scatter plot, or my favorite, you'll have to hang tight for this one, but it's worth the wait, I promise. This was, you can make a scatter plot or a scatter plot. Someone has made a scatter plot package in R, so then you can replace all your dots with cats, and there's all kinds of tweaks that you can make. And so make a scatter plot or a scatter plot. Anyways, you can look up the scatter plot package. I did not make any adjustments to these. They just came as the default examples, and I stole them, and here we are. You're right. This is beyond the scope of this course. I'm not familiar with this cat. I know it's a famous cat. Yeah, so this is where it's really obvious that I am older than you guys, and it's a little embarrassing. I was probably pretty close. But yeah, I know it's a famous cat, so Nyan cat. I think it's spelled like this, right? Nyan cat. But you're right, beyond the scope of this course in so many ways. All right. So just like before with histograms, right? We said, okay, if you're looking at a histogram, you need to have a normal distribution, and then you can talk about the center and the spread. And depending on if you have a normal distribution or a non-normal distribution, then you would have numerical measures of center and spread. And we're going to do the same thing, or a similar thing, I guess, with the strength and the direction of a linear relationship, which is the correlation. Okay? And so the I'll just go with what I have here. The correlation between X and Y. And I don't think we've seen correlation before, but I know that you've heard it in kind of regular language, right? It's on the news a lot. Oh yeah, there's a correlation here, and usually they use it incorrectly. And so there's a lot of things to be aware of. But in general, right, we talk about a correlation and we're relatively comfortable with what it means, right? So the correlation between X and Y is a numerical measure of the strength and direction of a linear relationship. Very, very important that it's for a linear relationship. Okay? The problem is that R or Excel or whatever you're using, if you ask for the correlation, it says, you got it. I can do it. And it will, right? And so you can always find the correlation, but it's only applicable if you have a linear relationship. Okay. And so here, we will always be able to calculate the correlation but it only applies if the relationship is linear. Oops. I'm going to steal from the textbook the correlation blurb. Oh, there's that little guy. All right. Where do you think? I think I skipped ahead too much. Maybe it's at the end. Sorry, please stay on the line. Some correlation facts. Correlation always takes values between -1 and 1. Okay? So it describes the strength of the linear relationship between two variables. And the textbook uses capital R, and I try to use the same notation as the textbook, but this is where I just can't shake it, or lowercase r. Not to be confused with the programming language R. But I'm sure it's all related somehow. Although I think R is called R because it's based off of S, which is a paid version that existed first, and then they made the open source RS. I think that's why. But also the link between correlation. Haha, the correlation with correlation. All right, so correlation, I like to visualize it on this number line between -1 and 1 with a 0 in the middle. Now, what's going to happen is a correlation of -1 is a perfect linear relationship, but with a negative slope, right? And so you've got a negative, perfectly linear, meaning they're all on the same line, right? And then on the opposite end, right, a correlation of 1 means that all the points are on exactly the same line, right? And so what we're gonna have, and maybe I'll bump this so it's on the same page here. First, here, we have a negative relationship versus, of course, a positive relationship. If the correlation is positive, you have a positive relationship. If it's negative, you have a negative relationship. And somewhere, so around 0, you have a weak relationship. And then as you move out towards 1, you get a strong relationship. Now, there's no hard rules depending on what field you're in. I know psychology has, I think, 7 different cutoff points here, and they have to memorize which one is no relationship, and then moderately weak, and then weak, and they just kind of go on and break it up. But I just go weak or strong, and then usually you'll probably find yourself wanting to say something like moderately strong or moderately weak, and that's totally fine. But in the beginning, I want to keep it nice and simple. So here we have strong relationships, and I would say the cutoff is roughly around 0.5, just for simplicity's sake. Sorry, negative 0.5. So anything, so a correlation that's between negative 0.5 and positive 0.5, I would classify as weak, relatively weak, moderately weak, whatever you like, or whatever it feels like. And then anything beyond that, strong, moderately strong, that kind of thing. Okay. And so a correlation of ±1 means all the points are on the same line. Yeah. Let's have a look at some examples here. Let's grab this. Just to get a feel for what these all look like. Okay, so here we have linear relationships across the board, so that's good. And a correlation of 0.33 would look like this. There, I would say there is something going on here, right? But it's quite a broad band. Here it gets a little bit tighter. and so on. And so here we have these positive relationships. The correlation is increasing. Notice 0.69 is still, we were classifying this as strong, right? But it's still quite a broad relationship here. So as a rule of thumb, what I usually say is, if you can see something, right? If you can see some sort of pattern, it's likely to be relatively strong or moderately strong, right? So when you see when we see a pattern, it is often classified as strong. Right. But if I was comparing the second one with the third one, obviously I would say this one is moderately strong and this one's strong, right? Or even very strong or something like that. Okay. Here, we had to push the boundaries a little bit to say, well, yeah, I could probably put some bounds on this and call it a relationship. Here it was more obvious. Right? So then here's a perfect relationship, perfectly positive linear relationship, correlation of 1. And here's a correlation of -1. And same deal, right? Here's a correlation of 0.08, which is very, very close to 0. Notice that there are lots of different ways that you could draw this line. Mainly like that. You could draw it like this. You could draw it like this. There's no anchor. When you have that situation, right, you have no relationship. Okay. So here, no relationship. Not R squared yet. But spoiler alert, R squared is just the correlation squared. All right. And then, of course, negative relationships behave the same way, but on the negative scale. Yeah, we will. Probably not today. Yeah. Do you guys all need R squared now? I mean, we can talk about R squared now. It's kind of a nice, let me see if I have, Sure. R squared, here we go. But I guess I'll wing it. So at your own risk, here we go. R squared. R squared is a goodness of fit measure. Okay, so R squared is a goodness of fit measure. We've heard goodness of fit before in the chi-squared scenario, okay? But which specifically tells us how good the model is at modeling the data, right? Just in general. Okay? So which tells us how good the model is at modeling the relationship between X and Y. By definition, and if you had to do a presentation, I would probably incorporate the definition of R squared because it is one of those things that I make you memorize. Usually it's later, but here we are. It's one of those things where you need to latch on to the definition and then eventually it'll start to make sense. Okay, and so the R squared definition goes like this. R squared is the percentage of variability. So R squared is the percentage of variability in Y explained by the least squares regression line on X. Explained by the least squares regression line on X, right? You can have multiple X's, right? If you move into multiple regression, you can have more than one X, but in general, the definition is the same. Are you doing multiple regression? Probably, yeah. So then you should use the adjusted R squared. Sure, let's write that down as well. In multiple regression, which means we have more than one X is all, right? So in multiple regression, we should use the adjusted R squared. Why? Because the adjusted R squared is going to penalize you for having too many X's in there, right? Of course, if you have a model that incorporates 100 things, oh yeah, but also what was the temperature that day? And what socks were you wearing, right? So it takes in too much information, right? Then you're overfitting it and it's less likely that that model is going to apply in general. Right? So the adjusted R squared is going to penalize you for having too many predictors or too many X's. So we should use the adjusted R squared since it will penalize you for incorporating too many predictors or X's, incorporating too many predictors, which are X's, into your model. Usually we would call that overfitting, right? Overfitting the model. Yeah.
Does that have anything to do with orthogonality?
So yes, that's when the variables are, so one is related to another one.
Something like that.
Yeah.
Like vectors are like, I don't know.
Mm-hmm. Yeah, they would be parallel.
Yeah.
Right. Yeah, so if a predictor is basically a linear combination of one or more other predictors, then you shouldn't include it because then you lose the orthogonality. But off the top of my head, is it related to R squared or the adjusted R squared? I don't know. But I'll think on it. Yes.
If we overfit the model, then it means we have a lot of
variance. That will result about variance.
So overfitting the model is when you make your model match your sample too closely, right? Because the idea is you want to be able to take a new sample and apply this model, and it should apply just as well. But when you're trying to capture every single little thing in your original data set, then you're overfitting the model, right? And so let's talk about, and I guess I'm almost out of time here, but pretty fun. So overfitting is when the model fits your sample data perfectly or very well, right? So when the model fits the sample very well, but doesn't apply to new data, right? Because you've said, okay, I'm gonna make a shirt just for you, right? And then I try to go and sell it in a store, that's not gonna work, right? Because I made a shirt that's perfect for you. I fit every aspect of you, right? And then, but then I try to give this shirt to someone else. Don't you love it? Well, it doesn't fit. Ha ha ha! I did it. So that's the idea. Okay. No, we usually don't have time. Yeah.
Do you have notes for that?
Yes, I do.
I have a project and I'm looking here because my project is
We usually don't get to logistic regression, but the textbook covers logistic regression, and I can post notes that I have for logistic regression because it is kind of different, right? But the only change is logistic regression, we use it when your y is a categorical variable, right? Yeah, because it's for categorical data, right? Or binary variables usually. Okay, I guess we're all out of time, but hopefully that was good. I'll stop this recording, but let me know if you have any questions.
Nope, thank you.
Thanks. And I'll stop this.